Let's go over the quotient rule for derivatives, and you're using these for functions that are in the form of, I don't know, f of x divided by g of x. Probably kind of obvious because that's what a quotient is. You just want to make sure that the function cannot be simplified into something that is easier than the quotient rule, because the quotient rule, in my opinion, is the ugliest of all of the derivative shortcuts. Air quotes. So here is the quotient rule. It's kind of bad. So the formal mathy way of writing it, if you want to find the derivative of f divided by g, it is g f prime of x minus f g prime over g of x squared. And in the quotient rule, the order of the numerator is very, very specific, unlike the product rule, because we are subtracting the two pieces, and subtraction is not commutative. So you absolutely must remember that the numerator of the quotient rule begins with your bottom function times the derivative of the top, then you subtract top function times the derivative of the bottom. So the numerator is very specific in the order that it needs to be written. Now within the individual pieces, like for this first product, it's okay to do f prime times g. And for this second product, it's okay to do g prime times f, because the multiplication part can be flipped. You just cannot swap the order of the entire numerator. Now that's the mathy way of writing it. The slang saying that is often associated with the quotient rule is where you call the numerator the high function and the denominator the low function, and then it can be read, the quotient rule is low d high minus high d low over low low. Kind of fun to say. And the d high just means derivative of the top function. High d low means the derivative of the low function. So same thing that I have up here, just written in a kind of a cutesy little way of remembering it. So let's do a few examples of the quotient rule. And the first one, we have a quotient of two polynomials. It's going to be kind of nice. That cannot be simplified to make the derivative any easier. So I'm going to dive straight into the derivative. And your derivative of the quotient rule is your bottom function. So I'm going to copy my bottom function. The derivative of the numerator will be 2x minus my top function, x squared plus 3. Now the derivative of the denominator, 3x squared plus 2. And then all of that is divided by your denominator squared. So low d high minus high d low over low low. And there's number one, and I'm going to stop there. We are not doing anything else with the derivative. I simply want you to show me that you can find the derivative, and later on in the year, we will work with simplifying these answers as needed. So number two, we have another quotient. This time my numerator is an exponential function. Denominator is polynomial. That cannot be simplified to easily avoid the quotient rule. I mean, you could avoid the quotient rule if you want, but the alternative, I think, is more difficult than the quotient rule. So my derivative, dy dx, will be my low function, low, x cubed plus 5. D high, the derivative of an exponential. The derivative of 2 to the x is 2 to the x times the natural log of 2. And that's when you just need to memorize that rule. So low d high minus high 2x. D low is 3x squared all over low low. X cubed plus 5 squared. I feel a sneeze coming on. Didn't happen. Okay. So there's that one. And again, I'm not going to worry about the simplifying of it. The one thing I will stress is please get in the habit of always putting parentheses around your derivative or your pieces in the numerator. So my low d high and my high d low, notice I'm putting parentheses around those. And sometimes it's not necessary. So like 2 to the x and 3x squared, that's all multiplication. So without parentheses, that carries the same meaning. However, x cubed plus 5, if you do not put parentheses around that and you only have this x cubed plus 5 and then 2x ln 2, now the entire x cubed plus 5 is not multiplied by the derivative of the numerator. It's only the 5. So I would recommend always, always, always using parentheses around your components for your quotient rule and the product rule as well, just because it's not wrong to have the parentheses, but it can be wrong if you leave them off. So I have one more example of quotient rule I want to look at, and we are going to do this one twice, actually, and I got these in the wrong order, so I'll start here. So this quotient rule, number 3, if I dive straight into the quotient rule, which we can because this is a quotient as it's written, this derivative would be low. So I'm going to copy my bottom function, d high, 4x cubed plus 2 minus high, x to the fourth plus 2x plus 1. D low is 2x, all over low, and x squared squared would be x to the fourth, but I'm just going to be lazy and leave it like that. That is a correct derivative. There's nothing wrong with that, and that is acceptable. However, you always want to be on the lookout for ways you can make the derivative a little bit easier, and for this problem, you can, and this is something that I call an STD. So an STD is the format of this fraction that allows you to simplify it, and an STD is what I am calling this because that is there we go, a single term denominator. If you have one thing in the denominator, and really the key is that you are adding or subtracting in the numerator, you can then split this fraction up as long as you keep your entire denominator intact. I can split this into x to the fourth over x squared plus 2x over x squared plus 1 over x squared. And if I do that, I then will create several different fractions that can be simplified individually. Plus 2x over x squared plus 1 over x squared. So here I saw that I had an STD, and I treated the STD by separating my fraction, and I am now reducing this even more. X to the fourth over x squared. 2x over x squared is 2 over x. However, I'll go ahead and write 2 over x. And then 1 over x squared does not reduce. And so now I've gotten rid of all of the ugly quotient stuff. I do still have x's in the denominator, but in both of those cases, because the numerator is just a constant, I'm going to bring those x's up and turn this problem into a power rule. And there is a little bit more work algebra-wise at the front end. However, the derivative ended up being significantly easier. And in my opinion, it's worth that extra work at the beginning to make the calculus easier. Some of y'all may prefer to go straight to the calculus and just have an ugly derivative and finish it in one step. But sometimes there are advantages to simplifying on the front end. So now I've changed it to a power rule. My derivative is going to be this. And I would stop there unless there is some benefit to moving those x's to the denominator and cleaning it up. So there are a few examples of quotient rule. It's kind of ugly. To me, it's the worst of the derivative techniques by itself. Hopefully that made some sense.